All right, these are two select problems from uh, section 3.7 in the textbook. This is number 21 and number 23, so page 221. Number 21, a Norman window is constructed by adjoining semicircle on top of an ordinary rectangular window. Find the dimensions of the Norman window of maximum area if the total perimeter is 16 feet. All right, so we're dealing with two equations here. We're dealing with the area of this figure and then the perimeter of this window here. All right, so let's talk about this diagram. So we have a window that has x width, has y height, and then the semicircle with the radius of x over 2. All right. So the two equations we're dealing with is going to be perimeter and area. We're trying to find the maximum area, so we're trying to optimize the area equation. So eventually, once we create the area equation, we want to get the area equation on the right side down to one variable. Okay, so let's talk about two equations here. We have the perimeter and the area. The perimeter is just going to be the distance around this entire figure. So we have x, okay, plus y, plus another y, plus this distance, this semicircle distance. So distance around the circle is called the circumference, but this is only half a circle, so this is only half a circumference. Circumference is half of 2 pi r, right? 1/2 the circumference is therefore 1/2 2 pi r. The 2's cancel out, leaving us with just 2 pi r, and then, leaving us with just pi r because the 2's cancel out. And then r is the radius of the semicircle, so the radius is going to be x over 2, so that we can try and limit the number of variables here. We just want to get this in terms of x and y for now. So x radius gets replaced with x over 2, so 2's cancel out, so we're left with x plus 2y plus pi x over 2. Oh, one thing that I want to point out is that the perimeter is just going to be this outer the outer border here. So the x, the y, and then the half circle. This is not part of the perimeter. So even though there's this this boundary that's connecting the semicircle and the rectangle, this is not going to be the perimeter that we're dealing with. So we don't worry about this portion here. All right, so that's our perimeter equation. Let's look at the area equation. So the area of this of the rectangle and the semicircle. Let's deal with the rectangle first. So length times width, so x times y, and then the area of the semicircle is going to be 1/2 pi r squared, right? So 1/2 pi, and then again the radius is represented by x over 2, so x over 2 squared. Simplify that to be 1 over pi over 8 x squared, because 2 becomes 4, 4 times 2 is 8, pi x squared plus xy. Now we want to optimize the area equation. So if we want to optimize the area equation, we want to get our the right side of the equation down to one variable. So it looks like the easiest variable to replace is going to be this y right here. Okay, since the x and x, there's two x's, and then we have x squared here. It's a lot more difficult to replace x. It'd be easier to replace y. So we want to replace the y using the perimeter equation. Now let's go back to the perimeter here. We want to solve for y. Let's see. We know the perimeter is going to be 16 feet, so we can replace p with 16. So 16 equals x plus 2y plus pi over 2x. I'm going to multiply everything through by 2. That way I don't have to deal with this fraction here. So if I distribute everything through with a 2, I get 32 is equal to 2x plus 4y plus pi x. If I solve for y, I can subtract 2x, subtract the pi x, divide everything by 4, and then simplify this expression to be 8 minus x over 2 minus pi over x over 4. Now I have an expression for y. Replace this into the area equation. All right, once I have this in the area equation, I can try and clean this up, and then eventually hopefully use the power rule to find the derivative, set the derivative equal to 0, and then find a critical point. So distribute the x through. We get 8x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. Once we have our equation separated and ready for us to apply the power rule, we can do that. So 8x becomes 8, x squared over 2, bring down the 2, which is bring down the 2, which is 2 here. The 1/2 comes out, so 1/2 and 2 times x, meaning that the 1/2 and 2 will cancel out. Bring down the 2, and we get pi over 4 times 2x. Bring down the 2x here in front, so pi over 8 times 2x. Here we have our derivative. Set our derivative equal to 0. And now it's just a matter of algebraically trying to clean all this up. So I found a common denominator here between two. Let's see. If I simplify the 8 prime a little bit more, so 8 minus x minus pi over 2x plus pi over 4x. If I find a common denominator here, which is going to be all over 4, another way that I can do this, I can just multiply everything through by 4. So that's another way to do this. But I'm just going to go through with what I have here. 8 minus 4x minus pi x over 4. By combining like terms, bring the 8 over. Cross product, divide everything through by 4 plus pi, and I get x is equal to 32 over 4 plus pi. So therefore, the maximum area occurs when x equals 32 over 4 plus pi, and y is equal to find the y, I can replace this x, plug this x back into an equation that will allow me to solve for y, so I can plug it back into this equation here. So 8 minus 32 over 4 plus pi minus pi times 32 over 4 plus pi over pi. Clean all this up, and y is equal to 16 over 4 plus pi. All right, 23, maximum area. A rectangle is bounded by the x and y axis. So you have the rectangle here bounded by the x and y axis. We have the graph of y is equal to 6 minus 2 over x. What length and width should the rectangle have so that its area is a maximum? So we're trying to optimize the area of this rectangle. Okay, so let's think about the area equation. The area of this rectangle is just x times y, right? X is the distance of this rectangle, and y is the distance, vertical distance. So we're trying to figure out along, if we were to create a corner along this graph, where's the maximum area going to occur? All right, so we have an equation now for area, but we want to get our equation down to one variable, so we can let's replace y. We know y is equal to 6 minus x over 2, so if I replace y with 6 minus x over 2, now I have my area equation in terms of purely just x, and can just simplify, clean this up, find the derivative, critical point. Okay, so if I distribute the x through, pull the 1/2 out, I have 1/2 times 6x minus x squared. Distribute the 1/2 through, I get area is equal to 3x minus 1/2 x squared. Next, we find the derivative so that we can find the critical point. So 3x becomes 3, 1/2 x squared becomes x. Set our derivative equal to 0. Solve for x, we get x equals 3. So we know the maximum area occurs when x equals 3. When x equals 3, then y must be equal to 3/2 if we plug 3 in for x. 6 minus 3 is 3. 3 over 2 is 3/2.